Back, this is GP. Today we are going to demonstrate embedding visualizations in TensorBoard as part of TensorFlow ecosystem. Before we begin the tutorial, it is essential to understand the origins of deep learning. The deep learning is a subfield of machine learning that is the branch of the artificial intelligence under computer science engineering. The genesis of deep learning models evolved from the neural networks, recurrent neural networks, convolutional neural networks, and deep belief neural networks. In the recent times, there are several innovatory deep learning models that are built based on generative adversarial networks and variational autoencoders. The significant developments of deep learning began in 1980s with the development of self-organizing map. In 1982, Hopfield network was constructed. The first Boltzmann machines were built in 1985, and the restricted Boltzmann machines were constructed in 1986. The deep belief nets were developed in 2006, and deep Boltzmann machine was constructed in 2009. The deep learning is applied to various fields of artificial intelligence, such as natural language processing, neural machine translation, machine vision, speech recognition, and object detection. The recurrent neural networks are applied to denoise speech signals to identify the speech patterns. A stack of autoencoders is applied in genomics with deep learning models to discover new drugs and understand the causes for diseases. To take the deep learning to the next level by pushing the limits of artificial intelligence, it is critical to understand why the deep learning models are the way they are today. Many researchers and developers of artificial intelligence built a deep learning framework inspired by the neural network architecture of the human brain. The restricted Boltzmann machines and deep belief net models were built to tear down the performance wall and computational workloads. Many of you already know me as a best-selling author on Amazon who published a couple of books on machine learning, deep learning, data science, high-performance computing applications, and few other topics such as in-memory computing applications. I also wrote around 400 research papers as an academic AI researcher with a vast number of big data tool installations on data science platforms with SQL and NoSQL databases, with practical machine learning and deep learning project implementations, applied mathematics, applied statistics, data analytics implementations with Tableau, Power BI, ClickView, and SAP Business Objects, for publishing with the universities as part of academic research programs. Currently, I'm working a video course, Mastering PyTorch for Advanced Data Scientists, to build millions of data scientists around the world for AI practice. I was also a public keynote speaker this year on Robotics and Artificial Intelligence Conference held at Los Angeles, California. I also published a couple of ebooks last year for SAP Leonardo IoT, the digital evolution of supply chain management with SAP Leonardo, sponsored by SAP. I published another ebook for Change Healthcare, that's part of McKesson's Healthcare Corporation, on machine learning and deep learning algorithms for enterprise healthcare. Building recommendation systems, designing, developing, and deploying machine learning and deep learning applications to solve the real-world problems in natural language processing, speech recognition, text-to-speech, and speech-to-text analytics is my experience. I also developed a number of machine learning and deep learning programs applying various algorithms and published articles with practical architecture and implementations on GitHub, Media.com, and Data Driven Investor. I have lots of experience with Python, TensorFlow, Caffe, Theano, Keras, Java, and all programming languages implementing stacked autoencoders, backpropagation, perceptron, restricted Boltzmann machines, and deep belief networks. Some of you may know me as a machine learning or deep learning or data science influencer recognized by Analytica and Keiko Analytics from the past few years consistently. but I actually happen to be also a chief data scientist for setting up AI strategy, neural network architectures, and application development of machine learning and deep learning algorithms for one of the largest Big Four consulting firms in the world. I also happen to be their SAP technical lead, integrating IoT platforms with SAP Cloud Platform. Before we begin the tutorial, it is essential to ensure that we have the necessary installations in place for running this application. You need to have Anaconda installed on your macOS or Linux operating system before we begin this tutorial. Once we install the Anaconda and set up the Python environment and activate the Python environment, you can actually able to go to Anaconda Navigator and either launch a Jupyter notebook or a Jupyter Lab notebook. And once you launch it, you'll be able to construct your application in a Jupyter notebook. And before you do that, you also need to ensure that you have actually installed TensorFlow on your machine. TensorFlow can be installed on macOS or Linux with several choices. You can pick up your mechanism of how you want to install the TensorFlow because there are multiple supported choices from TensorFlow. You can install through a virtual environment or a native pip command installation, or through Docker or installing from other sources. TensorFlow, as a best practice, recommends you to install TensorFlow by constructing a virtual environment. The virtual environment is basically a virtual Python environment that isolates from other Python development you must be developing so that it is actually not going to interfere and conflict with your programs. And native pip is another way of installing TensorFlow directly onto your system without even going through any container or a virtual environment systems. But because this is a native pip installation and it is not walled off, you may have problems with your regular Python application development. Therefore, it is not recommended by TensorFlow. You can also install through Docker, but again, Docker isolates TensorFlow from your pre-existing packages and Python projects. But again, Docker is only meant for large-scale distributed machine learning and deep learning. And when you install with Docker, actually, the Docker image you need to build, which could be quite huge, and it could take hundreds of megabytes for you to construct a Docker. Therefore, unless you are performing large-scale distributed deep learning applications, it is not recommended to leverage Docker. I already built separate blocks for installing Python or installing TensorFlow with multiple supported choices, which you can refer. You can find it on medium.com or on datadriveninvestor.com. Therefore, we're going to go and install the virtual environment, and that's how it is recommended for us to run this application so that it will be isolated. When you create a virtual environment, basically what you're going to do is you're going to start your terminal and run your application here, and you change your directory to TensorFlow. So you're already in TensorFlow application. So let's close this application and start a terminal application with a new shell. So you're going to change yourself to TensorFlow by changing the directory cd TensorFlow. And when you do that cd TensorFlow, you're actually in TensorFlow now. And you can activate your TensorFlow environment by simply activating the command source.bin/activate. And then when you see the TensorFlow in brackets, that means that your TensorFlow environment has been activated and the directory has changed to TensorFlow. Once you have this here ready, now you're able to construct your application in Jupyter Notebook. And you can go here and then you can start importing your libraries which are essential for your application, and you can run this here and you are able to import all the packages without running into any errors. So once you do that, you can actually see that here, and we're going to leverage MNIST dataset for this particular application. Again, MNIST is the most fundamental dataset that consists handwritten digits, and basically if you're already into machine learning, you might have used this foundational benchmarking framework dataset MNIST from several other applications. But again, the reason why we choose MNIST is because just like any other deep learning frameworks, TensorFlow also offers a pre-built data loader to load the MNIST from the built-in package of TensorFlow. That way you don't have to go to the internet and download it and load it into your application and all that. So basically, once you start doing that, you can actually import it from tensorflow.examples.tutorials.mnist by importing the import data MNIST, by reading the dataset method, by specifying the MNIST dataset here, and basically the MNIST dataset is already encoded with 1 hot encoding. Therefore, you need to enable when you read it with 1 hot equal to true. And then you can start importing your training size of the dataset, the testing size of your dataset, a validation size of your dataset, and all of that. And you can execute to see if you're able to. So TensorFlow basically is automatically reading the dataset from the internet, and then it is displaying you the size of the training dataset, testing dataset, and validation dataset. So once you have all of that ready, so basically it shows you 55,000 observations of your training. The data in TensorFlow is represented by tensors in a graph. The tensors are representatives for high dimensional data. In this example, the MNIST dataset we are using has 28 by 28 dimensions, which is 784 dimensions. The 784 dimensions is basically data points in R to the power of 784 space. As humans, we are only able to visualize, and we can see a lower dimensional data space, which is 3-dimensional data space. We can't see anything beyond 3 dimensions. Therefore, the interpretation of high dimensional data is very difficult from 784 dimensions. Therefore, the embedding visualization toolkit in TensorBoard gives us the ability to perform cursive by reducing the cursive dimension, but by seeing the tensors either by leveraging a principal component analysis technique PCA or T-distributed stochastic neighbor embedding TSNE, then we can visualize the data in lower dimensional space, in 3-dimensional space. So before we actually begin to construct the neural network, it is important we set the hyperparameters, because any hyperparameters that we set are not actually learned by the network automatically. It is something we need to default as constant every time we define a neural network. So here we're going to set the hyperparameters. Basically, we're going to create the path for the hyperparameters, and when you do that, you have to actually, it ends up creating a folder, logs embedding, to where all the logs for your TensorBoard are stored. You're going to initialize the learning rate by assigning 0.001 as your optimization learning rate, and then you're going to set epochs as 10, which are the total number of training epochs, and you're going to set the batch size 100 for each time it trains it as a batch, and you're going to display the frequency with 100. Basically, those are iterations. Number of iterations is the frequency of displaying the training results. And you're going to also set the network parameters. We know that MNIST is basically a dataset of handwritten digits containing 28 pixels in each dimensions. Therefore, we're going to set the height and the width as 28. So therefore, 28 multiplied by 28 is 784 dimensions. But for each dimension, that's what it is going to show in the dimensional arrays. Also, basically, MNIST dataset is nothing but number of digits. So you have the digits from 0 to 9. So that is what is total number of 10 digits. We're going to assign to number of classes as 10. And we're going to also set the number of units in the first hidden layer as h1 equal to 200. Once you set this and execute this block, now you assign and build your hyperparameters. So before we construct the actual graph, we also want to define few helper functions that help you to set the name and shape. So basically, when you do this, you actually have to create the weight variable function and a bias variable function. And then once you build these two functions with the simple inputs of name and shape and the return variable, you're going to actually have to construct a fully connected layer which takes the param x input from the previous layer for each iteration, and then it also has a parameter for number of units. In this case, the number of hidden units are set as 200, as we said it earlier, h1 equal to 200. And then you can also set the param name as a layer name, and then you can set the param use relu. If you want to activate the rectified linear units relu, you can activate the function with a boolean by adding relu non-linear or not. Once you add that, then you have constructed your neural network layer, and then now we are able to leverage all the helper functions we just defined earlier to construct our graph. To construct the graph, and then we're going to actually take the placeholders for input and output functions, and we're going to actually start filling the inputs and the outputs and the hidden layer. This is the fully connected layer we just created with inputs x, h1 as hidden layer, and you want to activate the relu. Use relu is true. Once we do that, and then we're going to define the output logics with fc layer again, fc1 and number of classes, output layer, and you don't want to activate the relu for the output. And then we're going to also define the loss function, optimizer, and accuracy for each iteration. So basically you're going to define the training loss and the optimizer. Here we're going to leverage the Atom optimizer with a learning rate, what we have defined as a hyperparameter earlier. We're going to specify the name as Atom optimizer, Atom op, and then you're going to define the accuracy for this. And once you complete the accuracy, then you're going to initialize the variables. You can execute this code of block here. So if it is not executing, there's something that's already running as a separate application. So basically we go back here and we launch the Jupyter Notebook again. Let's see what's going on here. Let's go to our TensorFlow directory and let's go to our application, and this is what we defined, embedding the visualization, and now again start importing. Import it, it's executed in the block, import it here, and the data has been extracted. Now you got your hyperparameters defined here, and then we're going to construct the helper functions, execute the helper functions. Now we are able to construct our graph, and we're going to run the graph. The graph has been successfully constructed. Now we're going to launch the graph. So basically here is when you launch your graph session, and when you do it, it actually is going to train your neural network in multiple iterations as we are defined with hyperparameters. So take this block, the next block, and start executing it. So you can see the neural network being trained now with training epochs 1 for each time. We have already set last time here as a display frequency 100. That's your iteration. So we go back and we see that's what it is running for each iteration in an epoch 100 times. And then you're going to see the accuracy of your training. This is the accuracy, and then this is the combined accuracy for all of your executions. I'm showing 94, and then 96.2, 97.1, 97.3, 97.6, 97.8, 98, and then for the 8th epoch it shows 97.7, and for epoch 9 it has a 97.8, and for the last epoch basically it shows the accuracy 98.2. So that is a pretty good accuracy in terms of the execution of the neural network. So the neural network has been trained with a high accuracy. Now we're going to have to create the embeddings for the neural network. And let's say we are interested in visualizing the tensor by activating the hidden layers in the test. So here is basically where we're going to do it. Is we're going to load the test set that we have assigned earlier and initialize the embedding variable with the shape of our desired tensor. So basically we're going to have 10,000 samples of test samples for 200 hidden units on the hidden layer. So those are the 200 nodes for the hidden layer. And then we're going to create the embedding variable with this shape of 10,000 by 200. And once you do that, you also have to create a metadata.tsv file that will store the index of each label for each sample. And once you execute it, you're going to actually be able to see this here in Jupyter Notebook. Your application is already running. But you can also run it actually on the tensor board for a much better visualization by reducing the cursor dimensionality. So we're going to just add the metadata and sprite files here because embedding projector is part of the TensorFlow, which is a Google's TensorFlow embedding projector. So we're going to set the embedding path data for the file name, and also we set the image file name so that this image you're seeing here with all the visualization will be stored to tensor board. So once we do that, then we can actually visualize these embeddings on the projector. Let's execute that. There have been no errors. Let's run our session to evaluate the tensor for embedding and saving the data. Once you run this, and then now you're able to run your session to evaluate your tensor, and you can also see the output. Basically, it has created the model cockpit for that visualization and saved to logs embedding folder, which we created earlier. Now we're going to start creating the metadata.tsv file and the sprite images as you saw earlier above, and then you're going to execute it. And once you execute it, it has created the files, and now you're going to reshape the images from vector to matrices by converting the multi-dimensional arrays by specifying the image width and the image height. And you're going to reshape the labels, and then again you have to specify the one hot encode to index, and you're going to write your images over here. And once you're complete, you can actually complete the testing, and then now you want to see your visualizations in TensorFlow. All you do is you go back to your terminal, start a new shell, and then just run your TensorFlow visualizations. And here is where your TensorFlow is running at a localhost 6066. So basically now it's reloading your T of logging pi. So I probably had already a graph event that I ran earlier, and it's showing that it is creating an additional event here. So once we go back here, now because TensorFlow is a Google application, the tensor board works much better on Google Chrome. So if you have a Google Chrome browser, it is best recommended you run on that so that you don't run into any errors. But if you do run into errors, you can reach out to me. I'll tell you what are the common errors coming from running the tensor board, and we can resolve those. You also may check Stock Exchange, where you may find some answers for some of the people who encountered some issues with running the tensor board with embedded projector, and you may find answers there as well. So we're going to go and run this on TensorFlow on a local host 6060 6006, and that's the embedding projector. So now you're able to actually see your digits. So these are all your 4s, these are all your 9s, and this is basically the tensor board visualization with the TSNE technique, where you're able to reduce the dimensionality of 784 dimensions, and we are able to see it in a 3-dimensional pattern. So now if you want to see all these digits with a specific label for each of them, you can actually start seeing them, label them, and now you can clearly see a segment and a cluster of the numbers floating around with specific clusters, so you can group them and you can clearly visualize them. So basically if you go here, so these are grouped as one, and you can also see over here, then you can see the 6 are grouped in green, and you can also see here the 4s are grouped in purple, and you can also see 9s are grouped here, and so on and so forth. So that exactly gives you, and finally you also can see some blues here in zeros. So that's pretty much how you run this application, and this is how you can construct it. Of course you can enhance the code, and if you want to add additional code, please feel free to download the code from my GitHub repository and enhance it and open source it as you feel appropriate. So once you have it, then if you run into any issues, just either send me an email or comment on this YouTube video. I'll be able to respond to you. Or you can also go to Stack Exchange, where you will find the answers for this application.